I've been photographing 3I/ATLAS every clear night, and what I'm seeing makes no sense. This interstellar visitor isn't acting like any solar system comet. One night, massive jets erupting in all directions. Next night, they disappear, replaced by a huge coma. Then it changes color, orange, then green. We don't know what it's made of. We don't know how Jupiter's radiation will affect it. Is this even a comet? Or something completely different? As it flies past Jupiter right now, the mystery deepens. Let's dive right in. So let me explain why what I'm seeing through my telescope each night is genuinely puzzling even veteran astronomers. Most comets we've studied throughout history follow a script. They're icy relics from when our solar system formed 4.6 billion years ago. As they swing closer to the sun, heat does its work. Ice vaporizes, creating those beautiful tails we associate with comets. We can analyze the light passing through that tail and identify exactly what chemicals are present. Water vapor, carbon dioxide, methane, each leaves a distinct fingerprint. Some comets visit every few decades, others take thousands of years, but they all share one thing: their family. They belong to our solar system. 3I/ATLAS isn't family. It's a stranger that wandered in from somewhere else entirely. This object formed around a different star, possibly hundreds or thousands of light years away. It traveled through interstellar space, the cold, dark void between stars, for who knows how long before gravity pulled it into our neighborhood. The fact that I can photograph something like this from my backyard telescope is almost absurd when you think about the cosmic distances involved. And yet, here we are, watching an alien visitor pass through in real time. But here's what keeps me up at night analyzing these images. We have absolutely no idea what this thing is made of. With normal solar system comets, spectroscopy tells us their composition within days. We know what we're dealing with. We can predict how they'll behave as temperatures rise. With 3I/ATLAS, we're operating in the dark. We call it a comet because it vaguely resembles one, but that's just our best guess based on appearance. The actual chemical makeup? Complete mystery. How those unknown materials react to solar radiation. We're learning as we go. Think about the implications. Different star systems create different chemical environments when their planets form. The ratios of elements, the types of ices, the organic compounds that develop, these vary based on the parent star's properties. 3I/ATLAS could be carrying materials that barely exist in our solar system. We might be looking at chemistry we've never encountered before. Now let me show you what's been happening in my observations, because this is where the real strangeness emerges. I've been imaging this object almost every clear night, and it refuses to behave consistently. One session, I'll capture it with a massive gas cloud, what astronomers call a coma, surrounding the nucleus. It looks almost peaceful, like a classic comet warming up. The gas extends far from the center, creating that fuzzy halo we expect to see. Then the next clear night, everything changes. The coma shrinks or vanishes entirely, replaced by these sharp, defined jets erupting from multiple points. Not a single jet from the sunward side like textbook comets show, but several jets firing in different directions simultaneously. When I process these images and invert them to see the gas distribution more clearly, there's no mistaking it. These are active venting events, not passive outgassing. The nucleus is expelling material in directed streams, and then it shifts again. Sometimes I capture both behaviors in the same night, a coma with jets punching through it. Other times, the jets dominate completely. There's no predictable cycle here. Solar system comets show consistent patterns because their internal processes are driven by consistent solar heating. But this erratic switching suggests something fundamentally different is happening inside 3I/ATLAS. Either its rotation is exposing drastically different surface materials, or the composition itself reacts to heating in ways we've never documented. The color changes make it even more confusing. Orange one night, vivid green the next. Sometimes both colors appear simultaneously in different regions of the coma. Green typically indicates carbon compounds breaking down under solar radiation, specifically diatomic carbon or cyanogen. Orange usually comes from sodium or certain iron compounds. But why would these appear and disappear between observations? Normal comets maintain relatively consistent coloration because their composition doesn't change. The fact that 3I/ATLAS keeps shifting tells us something unusual is happening. We just don't know what. And now it's approaching Jupiter, which adds an entirely new layer of complexity to this situation. Jupiter isn't just big. It dominates our solar system in ways that are hard to comprehend. You could fit roughly 1,000 Earths inside Jupiter's volume. But mass and size aren't the real story here. What matters is Jupiter's magnetic environment. Most people learn that Jupiter is a gas giant and imagine some fluffy ball of atmosphere. That's not accurate. Jupiter is primarily liquid metallic hydrogen. The internal pressure is so extreme that hydrogen, normally a light gas, gets compressed into a metallic liquid state. This creates a magnetic field that's absolutely enormous. Jupiter's magnetosphere extends 3 to 4 million miles into space, creating radiation belts that would kill an unshielded astronaut in hours. For comparison, Earth's magnetosphere extends about 40,000 miles on the sunward side. Jupiter's is roughly 100 times larger and incomparably more intense. 3I/ATLAS is passing outside the most lethal zones. But outside is relative when you're dealing with Jupiter. The planet's gravitational influence reaches about 35 astronomical units, billions of miles. Anything passing through that region feels Jupiter's pull. And we have historical precedent for what can happen when comets get too close. In the early 1990s, Comet Shoemaker-Levy 9 approached Jupiter on what seemed like a normal trajectory, but it was moving too slowly. Jupiter's gravity won the tug-of-war with the Sun's influence, and the results were catastrophic. The comet didn't just change course. Jupiter's tidal forces literally ripped it apart into at least 21 fragments. Those pieces continued orbiting Jupiter for a few years before spiraling inward. In July 1994, they slammed into Jupiter's atmosphere in a series of impacts that released energy equivalent to millions of megatons of TNT. Each impact created fireballs that rose thousands of miles above Jupiter's clouds and left dark scars visible from Earth for months. Some of those scars were larger than our entire planet. Could 3I/ATLAS suffer the same fate? The critical difference is speed. Shoemaker-Levy 9 was slow enough that Jupiter could capture it. Once captured, destruction became inevitable. But 3I/ATLAS is moving faster than any solar system comet we've studied. That velocity is its shield. The math works out. Its hyperbolic trajectory means it's going fast enough to escape not just Jupiter's gravity, but eventually the entire solar system. It'll feel Jupiter's pull. Its path will bend slightly, but it won't be captured. However, and this matters, we don't know how Jupiter's radiation environment will affect an object of completely unknown composition. We don't know if the powerful magnetic fields will trigger chemical reactions in the coma. We don't know if the gravitational stress during closest approach might crack the nucleus, exposing fresh material or creating new active regions. This is genuinely uncharted territory. Let me walk you through what I've documented across dozens of observation sessions, because the lack of any predictable pattern is itself the story. My first set of images showed predominantly coma activity. The nucleus was shrouded in this massive gas envelope. roughly symmetrical, extending far from the central point. If you saw just these images, you'd think this was a fairly normal comet responding to solar heating. Classic outgassing behavior. Then the second set showed a dramatic shift. Jets became the dominant feature. The gas distribution turned asymmetrical, clear streams of material shooting from specific points on the nucleus. The green coloration intensified in these frames, those carbon compounds becoming more active. When I processed these images to enhance contrast, the jet structures showed sustained, directed outbursts, not random puffs, deliberate venting from multiple active sites. The third behavioral mode was the wildest. Multiple jets firing simultaneously, Coma expanding and contracting, and in some frames you can actually see material shooting forward, ahead of the comet's direction of travel. That shouldn't happen with normal sublimation. Solar radiation pressure typically pushes material away from the sun, creating tails that stream behind. But here, gas is moving in directions that suggest powerful active venting, not passive heating responses. When I arrange all these variations side by side, one conclusion becomes unavoidable. This object cycles through dramatically different outgassing states in ways that don't match anything we've studied before. Something about its internal structure or composition causes these shifts, and we're documenting it in real time. Here's what makes this moment genuinely significant. We're watching an interstellar visitor interact with the most extreme planetary environment in our solar system, and we genuinely cannot predict what will happen next. This isn't manufactured drama. This is real scientific uncertainty. We've never observed an interstellar object's close encounter with a giant planet before. The sample size is exactly 1. Whatever data we collect over the coming weeks will likely inform planetary science and astrobiology research for decades. Because there's a bigger question hovering behind all of this. If 3I/ATLAS came from another star system, its composition tells us something about that system. If we detect unusual organic compounds, that informs our understanding of chemistry occurring around other stars. If material abundances don't match solar system ratios, that constrains our models of how different stellar environments create different planetary chemistry. Every interstellar object we study is a direct sample from somewhere else in the galaxy, delivered to our doorstep by cosmic chance. What happens during this Jupiter flyby might reveal properties we couldn't measure any other way. How does chemistry formed around a different star respond to extreme radiation? Do interstellar comets have different internal structures than our local ones? These questions feed directly into our understanding of how common the building blocks of life are throughout the galaxy. We're not just watching a comet pass Jupiter. We're gathering data that speaks to fundamental questions about planetary systems beyond our own. So here's what we know. 3I/ATLAS is an interstellar visitor behaving unlike any comet we've studied. Jets appear and disappear, colors shift, the composition remains unknown. And right now it's passing through Jupiter's radiation environment, an interaction we've never documented with an object from another star system. Over the next few weeks, I'll be tracking every change, capturing every shift in behavior as this plays out in real time. This is why I do this work, not to speculate wildly, but to document what's actually happening and share it with people who care about real space science. You're seeing the same data professional astronomers are analyzing, just explained in a way that makes sense. If you want to follow this story to its conclusion, subscribe to Galactic Breaking News and hit that notification bell. You'll know the moment I capture something new. Drop a comment and tell me what you think is causing those jets. And if this video added value, hit the like button. It helps more people discover this channel and join our community of space enthusiasts who want facts, not hype. Thanks for watching. I'll see you in the next update.